Yes, a three-phase 480 volts/208 volts tri-type transformer can be used as a step-up transformer to convert 208 volts to 480 volts. When using the transformer as a step-up transformer, the same wire sizing rules apply as when using it as a step-down transformer. The wire size must be sufficient to handle the increased current at the higher voltage. For a 4-wire grounded system, the step-up transformer will require a neutral wire connected to the secondary side, the 208 volt side, for the X0 connection. The X0 connection must be grounded to provide a reference point for the transformers and establish a neutral path for the circuit. For a 3-wire ungrounded system, a neutral wire is not required and the X0 connection can be left open. If the transformer is used in a 4-wire grounded system, the neutral wire must be properly grounded. This means that the neutral must be connected to the grounding electrode system at the transformer or at the service entrance. The voltage rating of the load must be compatible with the output voltage of the transformer. The transformer must be sized appropriately to handle the load current. Proper safety precautions and electrical codes must be followed during installation and operation. When dealing with electrical systems and transformers, safety and code compliance are paramount. Selecting the right components, employing correct wiring practices, and adhering to grounding principles are crucial for preventing hazards and ensuring reliable operation. Let's delve into more detail regarding transformer applications, wire sizing, grounding, and relevant safety measures. First, understanding transformer operation is essential. A transformer works on the principle of electromagnetic induction, transferring electrical energy from one circuit to another through a shared magnetic field. The voltage transformation ratio is determined by the turns ratio of the primary and secondary windings. In a step-up transformer, the secondary winding has more turns than the primary winding, resulting in a higher output voltage. Conversely, a step-down transformer has fewer turns in the secondary winding, reducing the output voltage. When repurposing a 480 volts/208 volts transformer as a step-up transformer, you are essentially reversing its intended operation. The original secondary side, designed for 208 volts, becomes the primary input, and the original primary side, designed for 480 volts, becomes the secondary output. This is perfectly acceptable as long as the transformer's volt-ampere rating is not exceeded and the appropriate wiring and grounding practices are followed. Secondly, wire sizing is a critical aspect of electrical installations. The primary consideration is the ampacity of the wire, which is its current carrying capacity. The National Electrical Code, or NEC, provides tables, such as Table 310.15b16, that specify the allowable ampacities of various conductors based on their size, insulation type, and installation conditions. When using a transformer as a step-up, you must calculate the current on both the primary 208 volts and secondary 480 volts sides. The wire size must be adequate to handle the calculated current without exceeding its ampacity. For example, if the secondary side of the step-up transformer is expected to deliver 20 amps at 480 volts, you must select a wire size that is rated for at least 20 amps at its temperature rating. Similarly, the primary side, which is operating at 208 volts, will draw a higher current to supply the same power. Therefore, the wire size on the primary side must be larger than the wire size on the secondary side. Always refer to the NEC for specific wire sizing requirements and derating factors. Thirdly, grounding and bonding are essential for electrical safety. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protective devices, such as circuit breakers or fuses, to quickly trip and to energize the circuit. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. In a 4-wire grounded system, the neutral wire plays a critical role in providing a return path for unbalanced currents. The X0 connection on the transformer is the neutral point, and it must be grounded to establish a reference point for the system. This grounding connection is typically made at the transformer or at the service entrance. The grounding electrode system, which includes grounding rods, ground rings, or metal water pipes, provides a connection to the earth, ensuring that the system is properly grounded. In a 3-wire ungrounded system, there is no neutral wire, and the X0 connection can be left open. Ungrounded systems are sometimes used in industrial applications where continuity of service is critical. However, they are more susceptible to transient overvoltages and can be more difficult to troubleshoot. Fourthly, consider the impact of harmonics. Harmonics are distortion in the voltage and current waveforms that can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause overheating of transformers, conductors, and other electrical equipment. If the transformer is supplying a significant amount of nonlinear loads, it may be necessary to use a K-rated transformer, which is designed to withstand the effects of harmonics. Furthermore, regularly inspect the transformer for signs of overheating, such as discoloration or deformation of the windings. Check for loose connections, which can cause arcing and overheating. Ensure that the transformer is properly ventilated to prevent excessive temperature buildup. Use thermal monitoring devices to track the temperature of the transformer and identify potential problems before they lead to failure. Keep accurate records of all maintenance activities, including inspections, repairs, and upgrades. This documentation can be valuable for troubleshooting problems and planning future maintenance. Another critical factor is the overcurrent protection of the transformer. Overcurrent protection devices, such as fuses or circuit breakers, are designed to protect the transformer from overload and short-circuit conditions. The size of the overcurrent protection device must be carefully selected to protect the transformer without causing nuisance tripping. The NEC provides specific rules for sizing overcurrent protection devices for transformers. These rules take into account the transformer's volt-ampere rating, primary and secondary voltages, and impedance. In general, the overcurrent protection device on the primary side of the transformer should not exceed 125% of the transformer's primary current rating. The overcurrent protection device on the secondary side of the transformer should not exceed 125% of the transformer's secondary current rating. However, there are exceptions to these rules, so it is essential to consult the NEC for specific requirements. In addition to overcurrent protection, it is also important to provide proper surge protection for the transformer. Surges or transient overvoltages can be caused by lightning strikes, switching operations, or other disturbances on the electrical system. Surges can damage the transformer's insulation and windings, leading to premature failure. Surge protection devices, or SPDs, are designed to protect electrical equipment from surges by diverting the surge current to ground. SPD should be installed on both the primary and secondary sides of the transformer to provide comprehensive surge protection. When selecting SPD, it is important to choose devices that are rated for the appropriate voltage and current levels. The SPD voltage rating should be higher than the nominal voltage of the system, and its surge current rating should be high enough to handle the expected surge currents. Finally, ensure that the transformer is installed in a location that is accessible for maintenance and inspection. The location should be well ventilated and free from moisture and dust. The transformer should be mounted on a solid, level surface and secured to prevent movement. Consider the ambient temperature of the location. Transformers are typically designed to operate within a certain temperature range. If the ambient temperature is too high, the transformer may overheat and fail. Provide adequate ventilation or cooling to maintain the transformer's operating temperature within its specified limits. Also, consider the potential for exposure to corrosive substances. If the transformer is installed in a corrosive environment, it may be necessary to use a specially designed transformer with corrosion-resistant materials. Properly labeling the transformer and associated equipment is crucial for safety and maintenance. Clearly label the transformer with its voltage ratings, volt-ampere rating, and other important information. Label all associated switches, circuit breakers, and other equipment with their functions and voltage ratings. Use warning signs to alert personnel to potential hazards, such as high voltage or arc flash. Effective labeling helps prevent accidents and ensures that personnel can safely operate and maintain the equipment.